Clément on stage. Thanks.
Hi, everyone. So, as Mathieu said, I'm a bit of a different speaker, like Julien this morning, but I'm sure we have plenty of things to talk about together, especially seeing how many of you are interested in less bugs in your code. So my name is Clément Bourgeois. I work at AdaCore, and we do Ada software. Don't raise your eyebrows yet. I mean, I can see them, but still, I know it's weird for you. But I'm going to talk about languages in general, started from Objective-C, Swift, and going into Ada and Spark, and seeing how safety critical is related in the evolution of languages. So first of all, some context. What's safety? Safety is when the software must not harm the world. That might sound like pretty scary, but that's actually it. When you have software in a plane, if the software has a failure, you can lose lives. But you can look at the definition in any way you want. You can look at it broadly. You can say, hey, if my software has a failure, well, I can lose money. Maybe my company can be jeopardized. That's also something that can be really safety related. And in that domain, choosing your programming language is really important. What do you look for in a programming language for safety? Well, you want it to be reliable, which means most of the time you spend is reading the code, and you want it to be easy to read and to understand. You want to avoid any pitfalls, especially. You want it to be analyzable. So if you can have any static analysis, that's a plus. Control flow analysis, that's amazing. If you can do formal proofing, well, you're a king. Predictable, you must be able to analyze stacks, heap, to see that your constraints in time and memory are something you can know even before the execution. But you're here saying, why do I care? Well, safety is not something that's only for us. It's always true that finding a bug and fixing it early in the development process is less costly. As you can see on this really precise chart, it's cheaper. And if you have a language that gives you more information early on, well, that's a huge benefit. On iOS, when you submit an application, you have to wait for the overhead of the approval of Apple. Well, sometimes having a buggy application on the App Store can be a problem for you. Maybe if you found that bug earlier, well, you could have avoided that few days of something buggy for the user. So now let's look a bit at Swift itself. How is it safer? Is it safer than Objective-C? Well, first of all, you have the syntax. And in the syntax, Swift chose to avoid all the common pitfalls you have in C by removing shortcuts. You have to have curly braces in your code. Here you have a bit of C code. And this is a bug that was in the FreeBSD OS. And the guy who was coding it was maybe doing Python, I don't know, but the second statement, function call, is not within the if statement. Well, in Swift, you have curly braces. So with curly braces, you avoid that, and that's something that might say, oh, but I have to type more characters, that's a pity. But hey, it doesn't take that much of a time, and you got rid of a very nasty bug that might be hard to find. And you get rid of the infamous break statement that can also cause plenty of bugs. You know, maybe the go to fail SSL bug for iOS. Let's move towards typing. Typing is something that's stronger in Swift, you know that. But how is that safer? Well, you have the reliability that any variable has a type that's static. It cannot move. And what does that provide to you? Well, that provides you more compile time error detection. And it's something that's great, because that's more information for you. You can fix something earlier and remember the graphs. That's exactly what you want to be doing. And also, you get rid of many C-inherited undefined behavior that you can find in Objective-C as well. For example, you have casting pointer types from one to another. That's an undefined behavior. You have null pointer dereferencing. You have the order of operand analysis. Here, that's something perfectly valid in Swift. It was always evaluate to 4. If you do the same syntax in C with increment-decrement operators, well, it's undefined behavior and unspecified specification. And also, Swift wants to remove the decrement-increment operators. I don't know if it did that already. In general, more runtime checks. Runtime checks are really good because you get an error and you're able to react after it, like in an overflow case. Something really amazing in Swift is the enums. They're not a shorthand for integer like in C. They're like their own type, and which means you cannot go too far away and just assign a value that's meaningless for the enum type. Also, switch statement must be exhaustive. You cannot forget a case. And a really, really interesting thing that was introduced also in Objective-C because the development was done earlier than Swift is the automatic reference counting that guarantees that you have no pointer pointing to invalid data in your program. Okay, so I chose to focus on this aspect of Swift. What about Ada? Well, can you raise your hand in the audience if you've heard about Ada? Woo! Can you raise your hand if you've done Ada, programming in it? That's okay. Can you raise your hand if you've done Ada in the last 5 years? Whoa, wow, amazing. Well, it's, you might say it's that defense language that they used to have in the 80s. It's bloated, it's non-usable. Well, first of all, it's a general purpose language. It's designed for a long-lived system, and it has keen interest in low-level programming. And it's been standardized in 1993, but it's actually alive. We have revisions in 1995, 2005, and 2012. And we have all the modern features you expect in a language, which are while loops, if statements. No, I'm kidding. We have generic templates, concurrency support, and programmation by contracts. And the last point I will talk about quite a bit in detail in the following minutes. And Ada has quite a lot of similarities with Swift, but it goes further than Swift for critical software. Where is Ada used? What do we do when we work around the Ada language? Well, we do this kind of stuff. Ada is in Ariane 4, 5, 6. It's in Boeing. This is a 787 Dreamliner, F-22, Ligne 14, and it's in New York as well. And this is an artificial heart pump. So it's designed around aerospace a lot, trains, transportation, any place where if the software fails, well, somebody can die, or it's really critical, even in finance as well. So what extra safety is provided by the language itself? Well, let's talk about the syntax. The syntax is something that should not be overlooked, and the Ada syntax can be called really specifiable. So here you have a bit of Ada code, and so you see the verbose is quite intense. It's looking like Pascal code. What I want to focus on here is the extra information that I mean by specifiable. Everything you write provides more information for the guy who's reading the code and for the compiler specifically. Here you have an out parameter, which means it's passing by reference, but more than that, we won't read what's in result. We'll just write to it. And that's something the compiler might check statically. Also, in that philosophy, we have a different assignment operator. It's different than equality. Well, it means that there is no, you cannot, like, by mistake, use one for another. And in also the syntax part, we have integer literals, and that really helps when you want to write any number in a complex base or something that can be hard to read, even in base 10. Typing. So to compare on the typing, Ada is something that doesn't exist in Swift, which is ranges. You can give more information about your type by saying, well, it's going to be an integer, but actually it's going to go from 1 to, well, the last of integer there is in the integer type. And your type is going to also have that last property that's going to be the same as integer, and you're going to have the first, which is going to be 1. This is really useful because it's meaningful information, and you can make all kind of analysis based on that new type. For example, if you're developing a software for a car, well, you know your speed is going to be most likely between 0 and maybe, I don't know, 200 miles per hour. Well, in that case, you can have a pretty defined constraint on your type. And that's something that's helpful because you can detect an error, and even statically or dynamically. No type inference. That's a big philosophical difference with Swift. You have to declare the type all the time. It's not inferred on an assignment, for example. So it's you write more information, but you also specify more information. And there are equivalent enumerations. You have a first-hand type. It's not a shortcut for anything. And you declare it like this. Now I'm going to talk about something I mentioned a few slides ago, which is contracts. Contracts is something that comes in Ada 2012, and it's a way to specify the behavior of your function. What you're going to do is you're going to write a precondition and a postcondition on your function. Why would you do that? Well, because sometimes this condition, so the precondition will be evaluated when you enter your function, and the postcondition will be evaluated when you exit your function. And sometimes it's easier to write the check for the function than to write the implementation. Here we are sorting an array. And well, it's pretty straightforward to write that my array is sorted. Here I have a for loop that's gonna go through the array and make sure every element is inferior or equal to the one coming after it. But the implementation, as you all know, it's really famous in the industry now. You have to do it on a whiteboard and get hired or not. So that's something that can be a bit tedious. And once you have that written down, if at any point you have a failure of those contracts, well, you're going to be able to isolate where it's coming from. Also, you have restrictions. Sometimes you don't want to use all the fancy features of your language because it's not as safe as you want to. So Ada has restrictions like no dispatch, no allocators, that allows you to remove some part of the feature and to actually get a subset of the language to use. Why is a subset interesting? Well, because of this. We have something that's called the Spark language, and it's a subset of Ada. And it's the same sort of thing I've written just before, with a bit more specification that it's in Spark. And with Spark, what we're able to do is prove, and I mean prove, like it's proved, there is no runtime errors. So when you run Spark on some Spark code, which is a subset of Ada once again, you will see, the prover will detect whether there are runtimes that are possible in your code. And more than this, it's going to prove whether the behavior you specified in your contract is actually true, whether you actually sorted the array in all conditions at all time. And it's not a fuzzer. It doesn't feed all the testing inputs. It mathematically proves that the conditions and all the information you provided here is true. And it also uses all the extra information provided by Ada, like the ranges I took before and the more specifiable syntax. And Spark is something that's also interest for the industry. It's going to be in Ariane 6, and we have a small student satellite project that was around the Earth for quite a few days that used Spark as well. And it was like the only satellite to stay there that long. And once you run Spark, well, it will say, all right, your postcondition is proved. You actually know how to sort an array in all cases, all the time, and it will never fail. So to conclude, this is just to say that in terms of safety, Ada provides more than Swift, but Swift has the advantage of a bit more expressivity. And when it comes to speed, well, it depends on what you're doing. Also, all tooling at AdaCore is free software and open source. So if you're interested in just looking at Ada, you have compilers, IDEs, Spark. Go to libre.adacore.com. Thank you so much.
Thank you. Thank you. So, I'm not writing airplane software, and I'm not writing like hard pump software. So why should I care? Like, is it really important for people writing regular code, or?
It's important when you come to a point where you see that you spend a lot of time fixing bugs, and we've seen that today. We had the talk from Bruno about the testing, and I think that's going in the same direction with other solutions.
Yeah,
if you combine safety of language and the testing, then overall it comes to reducing the number of bugs.
But the questions that pops at this moment is, if I go in that direction, if the languages go into that direction, won't it be harder to write code, actually, and to spend more time writing code?
Well, the time you can spend writing code is actually some time you gain afterwards, because that's time you don't spend fixing your bug or just having that extra headache about something that's not working, because you fixed it beforehand, taking a bit more time, writing your contract, writing something to help you in the future.
So do you find yourself like writing less tests after all? Like, do you find yourself like writing less tests code after all?
We write still quite a lot of tests, but it's way easier to pinpoint and to focus on the edge cases. Thanks to all that extra syntax.
Yeah, one thing I want to add or to emphasize is this contract strategy that is used with the Spark specifically is not just like writing tests, where when you write tests or unit tests, acceptance tests, whatever, you take some data, some relevant data, and you try to exercise your code with this data. Whereas this approach is a bit different, because it seems that you really write some kind of mathematical conditions that needs to be matched. So that's really different, because you will actually not need to provide data or use that.
Yeah, exactly. The contract you wrote is transformed into a verification condition, and the prover will make sure it's always true. And if it's not, it will tell you, well, I have that case where it's not true. Check it out.
Yeah, and it seems almost magical. But do you think that kind of approach would come to us someday soon?
It really depends on the language you're using. Swift has some tools for it. I don't really know the state of the art of the static analysis in Spark in Swift. I mean, but it's yeah, it might be a good language actually to go in that direction.
Yeah,
Do you feel afraid when you go back to a unsafer language?
Well, it depends on what you do. Once again, sometimes you don't find the need of being safe because there's no need for it, and that's fine. We don't do all the same programs, but
yeah, when you're rendering just a simple web page, maybe you don't need over security stuff. But what's interesting is it seems that the compiler, the tools are actually working for us. Like they help us to do that. It's not more complex to write Swift code than to write Objective-C code. We could even say that it's easier. I don't want to start another flame war, but it's easier. It's quicker to write Swift code than Objective-C code, and yet the code that is finally made is inherently safer. But that's
yeah, and I mean, we only had Swift talks today, and I guess the time you lose because the compile time is longer, maybe I'm sure you gain it some other way. So
yeah, does that affect your daily productivity, like having a compile time which is a bit longer?
It's as I said before, it's something it's a trade-off, and overall, I think the trade-off is positive, especially for what we do. It's extremely important.
Yeah, and especially that, as you said at the end, like it doesn't seem that it's longer. Like it doesn't cost. It costs during compile time. It doesn't cost at runtime or not much, right? That's
and I mean at runtime, if you want to be blazing fast, you can use the restrictions, remove some features of the language. If you use dynamic dispatching in Objective-C, you're gonna be not faster than Swift or Ada. And if you wanna go blazing fast, you can always choose what you want specifically.
All right. Okay. Yes.
Okay.
So
Thank you very much. Thank you for your talk.